The contents of this topic will be first study about the latches. The latches are nothing but unclocked flip-flop. Unclocked flip-flop. That means if you take a flip-flop and remove the clock signal, this is called latches. And in the flip-flop topic, study circuits of each flip-flop. Then we study about the truth table. Truth tables are nothing but the output and input combinations. And characteristics table. Here the characteristics table is nothing but the extended version of truth table. We can say extended truth table. Okay, and that means using characteristic table or extended truth table we can able to design the characteristic equation. So the characteristic equation can be derived from the characteristic table by the use of K-map. Then after we study about the excitation table. It's a new concept, excitation table. The excitation table is actually useful to convert one flip-flop to another flip-flop. Okay, and the excitation table means for a particular set of output. Okay, if you need to get this output, what are the combination of input you need? That means the left side will have output and the right side you should have the input. Okay, after studying the excitation table we'll study the conversion of flip-flop. That means if you have one flip-flop, how to use that flip-flop to make another to create another flip-flop, we'll study about here. Okay, after studying this thing we'll study about some examples of flip-flop. The output of inverter is connected to the input of like this. Okay, this is a latch. Okay, latch means to lock something. Output is locked. That is why it's called latches. And you can see here they have only one input line. Okay, so as they are having one input line, where to give the clock pulse? That is why we use the NAND gate, okay, and the NOR gate. Okay, so these two gates are the universal gate. That is why to design the latches or the flip-flops we use NAND gate and NOR gate. So remember, for NAND gate and for NOR gate, okay, design is quite similar. And remember thing, enable and disable. Okay, for the NAND gate, enable is 1 and disable is 0, and just opposite in the NOR gate, enable is 0 and disable is 1. So this is the basic difference. That means if I have a flip-flop, okay, this is my Q and this is my Q complement. For example, this flip-flop is made up of NOR gate, and if you want to create this flip-flop using NAND gate, this is nothing but this is a flip-flop, okay, and this is NAND gate. This becomes Q complement and this becomes Q. That means if you change the position of this Q and Q complement, you will change the internal circuit. Flip-flop are the basic memory elements. So whenever you think about to create some memory which can store the data or information, you should also always think about the flip-flops. That means the flip-flops are a basic building block to create memory. Each flip-flop has the ability to store only one bit of information, right? And if you think about a flip-flop, it is having two output. So one output is the normal output, okay, and the other one is the complementary output. Okay, that means whatever you're getting here in the normal output, let it name as Qn, and the complementary should be Qn complement, right? So whatever, if you get 1 here, you'll get 0 here. If you get 0 here, you'll get 1 here. Okay, and vice versa. And each flip-flop is having two states. Very important. The flip-flop having two states and both the states are stable. That means if you go to the first state and it will remain in the first state, and if you go to the second state, it will also remain in the second state unless and until you change the input. That is why as the both the states are stable together, that is why it's called as a stable multivibrator, right? So the flip-flop also can be used as frequency divider. Okay, frequency divider. let me take an example. So let's consider this is an inverter, this is the another inverter, okay, and the input inverter 1, inverter 2. So the input of inverter 1 is equal to the output of inverter 2, and the input of inverter 2 is nothing but the output of inverter 1, right? If these inverters are connected in this format, if you see here, if you give 0 here, right, if you give 0 here, the inverted output of first inverter is 1, and this one is again fed to the input to the inverter 2, and the output becomes 0, and which is also fed to inverter 1, so output always remain 1 of the inverter 1, and output always remain 0 for the inverter 0, right? That is why we can see if this 5 volt level 0 to 5 volt, so the output of inverter 1 is always high, and output of inverter 2 is always low 0 volt. Okay, so you can see in the circuit, without giving any information in the input lines, or without adding any information to the input lines, the output of inverter 1 always remain in the high state, and the output of inverter 2 always remain in the low state. That is why both the states are stable state. You can say this is as astable multivibrator. So in this flip-flop chapter, we will study some more concept